Hi folks, welcome to the last part of this week's lesson. So now we're going to take a sharp turn and we're going to go into a whole different area. Although we're going to see that we're going to need those characteristics of vectors that we developed in that first part of the course. And what we're going to start to do is essentially analytic geometry in 3 dimensions. All right. And when you were studying analytic geometry in grade 9, and then a lot of what you did in grade 10 involved working with lines in 2D. Okay, and here we have the standard equation of a line in 2 dimensions. And so what we'd like to do is we'd like to generalize the equation of a line in 2D into 3D. Okay, so here what I'm asking for is what would be the natural generalization for the equation of this line. So, I suppose a natural thing to want to write is to say, well, I have ax plus by, but now we're introducing a z component, so would that be cz and then say equals d? Okay, so this would be really nice because it's the exact same format as the 2D format, but includes this z component, and hopefully that were to give us a line. All right, so let's try to figure out if this is going to be the case. So let me pick some easy versions. So let's say I pick x plus 2y plus z is equal to 4. Okay, so a is equal to 1, b is equal to 2, c is equal to 1, d is equal to 4. All right, so I give you a bit of a hint here. I say find 3 points on that satisfy this equation. Now, if those 3 points are on a line, okay, say point A, point B, point C, or I guess I'll call them P, Q, R, okay, since we're already using A, B, and C. Well, if they were all along the same line, then what we could do is take the vector PQ and the vector QR, and those 2 vectors should be collinear, all right, or parallel to each other. So let's see what happens. So let's pick 3 points. So let's say point P. So let's pick something easy here. Let's say I pick x equals 1, okay, then say y equals 1. So I have 1 plus 2 is 3, all right, and let's pick z equals 1. That's going to give me 4. Okay, 1 plus 2 plus 1 is equal to 4. So there's 1 point on my whatever this represents. Okay, let's find some point Q. So let's say we make x equals 0. Let's make y is equal to 1 again, so 2 plus, so we would need z to be equal to 2. So because these numbers are nice, it's easy to come up with points. So 2 times 1 is 2, plus 2 is 4, and let's come up with a third point. Let's say we let x be equal to 2, y be equal to 0. Okay, so 2 plus 0 plus 2, I'm going to need z to be equal to 2. Okay, so here are 3 points on this, object, whatever it is, possibly a line. So let's see what happens. So let's use this idea that if they were on a line, I should be able to form vectors PQ and QR, and they should be parallel to each other. All right, so let's check that here. So let's do vector PQ. All right, so remember second minus first, so 0 minus 1, negative 1, 1 minus 1 is 0, and then 2 minus 1 is 1. And now let's find the vector QR. Okay, 2 minus 0 is 2, 0 minus 1, negative 1, and 2 minus 2 is 0. And when you take a look at these 2 vectors, I think it's very clear that these are not parallel to each other. All right, so that must mean that this type of equation, while it would have been nice if it represented a line in 3D, it clearly doesn't, because we found a counterexample. All right, now before we move on to try to come up with an alternative way to define a line in 3D, something that's going to work, I'm wondering if you might remember where we've seen an equation that looks something like this before. All right, and we've seen something like that before. If you remember the question where we said, let's say I've got points P and Q, and I want to find all points that are equidistant to those two, okay? So this point is equidistant to those two, and this point is equidistant to those two, and this point right in the middle is equidistant, and that one's equidistant, okay? Well, when we solved that problem, we came out to something that looked like this equation here. So you can go back and check. It was something of the form ax plus by plus cz plus d plus cz equals d, okay? But as I'm drawing all these examples, it kind of looks as though this is forming a straight line, except this is when you realize that this point up above could also be equidistant to P and Q, and this one up here. In fact, let's see if I can show this a little more. Let's assume that the 2 points are at the tips of these pens here. So this point in between and this point in between, this point equidistant, okay? And this point here equidistant. So we can, again, create that line that I drew there, but then that point up here is also equidistant, okay? And then another point up here, which is the same distance to both points. And I asked you to think about that. And if you think about it, it's not a line, it's going to be a whole plane's worth of points, okay? So let's see if we can, a little tough to see here, but what you have, and this would continue on forever, there's a whole plane's worth of points that are equidistant to these two, because there's these down the middle, but then there's these here, okay? And you realize that it's going to create the plane between those 2 points. All right, so this is already giving us a precursor as to what's to come. That this basic equation that in 2D represents a line, the 3D version is not a line, but it's going to represent a plane. Okay, and this is what we're going to spend a lot of our time on later on. All right, so this is where we still presumably want to study lines, because what did we do? We studied lines to represent, motion in a straight line. Okay, then we ended up with 2 lines and we wanted to see how they intersected, because if I want to create, say, a triangle, it's 3 lines that intersect. So I definitely still want to determine a way to describe a line in 3D. Okay, and so here what we're going to do is I'm going to consider our other way of expressing the equation of line, and that's slope-intercept form, okay? And remember what the slope gave you. The slope gave you the rate of change of y with respect to x, okay? So if I have my line here, I take a look at this ratio of how y increases or decreases every time x goes up by 1, okay? Problem is that in 3D, there's no easy way to represent the idea of slope. Because if I have this line here, well, is it how z increases with respect to x and y? In which case, you can't easily write a single ratio to represent the steepness of the line, okay? So we're going to need something else that represents the steepness of a line, okay? So we're going to stick with 2D for now, okay? And see if we can come up with an alternative to the idea of slope that'll generalize a little better when we try to bring it up to 3D, okay? So let me take some line here. And so let's think of what we have that could represent the steepness, or maybe this will give you a bit of a hint, the direction of the line, okay? We think of this not so much as to how steep it is, steeper, less steep, is think of this as the direction of the line. So what we're going to use is, instead of a slope to represent the direction of the line, well, we're going to use a vector that's parallel to the line. Okay, we're going to call it a direction vector, not surprisingly. And because it has a very similar uh, use as the slope, I'm actually going to use m as the symbol for that vector. All right. So instead of using this ratio, which represents how y changes with respect to x to represent the direction of the line, I'm going to use a vector that's parallel to this line. Okay. But of course, what I want to do is I want to use this to write any point on this line. Okay, so similar to what we had before, when you wanted to find the equation of a line, you needed the slope and you needed a specific point. It could have been the y-intercept, but in fact, it could be any point on the line. So I'm going to assume that I need the same thing because this is not the only line which is parallel to that direction vector m. This is also parallel. This is also parallel. This is also parallel. So similar to before, I'm going to need a specific point on the line. Okay? But because I want to work with vectors, I'm not going to be working with this point, but the vector from the origin to that point. Okay? And this is going to be called R naught. Okay, so you know the way we use x naught, y naught to represent a specific point on the line. This is going to represent the vector to some known point on this line. But what I want to do is I want to use this known point and that direction vector to define any point on this line. And maybe you can see it here, is if I take the vector to R naught, my known point, and I add tip to tail, well, not necessarily just this direction vector, but some multiple of this direction vector, look where I end up with on another point on the line. So this vector, which I'm just going to call R, which represents any point on the line. And say the point that I'm trying to represent is here. Well, I can do the same thing. I can do R naught plus some scalar multiple of my direction vector. In this case here, the scalar multiple would be a negative scalar multiple. If this was the point I was looking for, again, R naught plus some scalar multiple of my direction vector. And if I take all the possible scalar multiples of my direction vector added to R naught, I can describe any point on this line. So the way we give a new type of equation for the line in 2D is R is going to represent the vector to a general point on the line is equal to R naught, the vector to the known point, plus some scalar multiple of my direction vector, exactly what I did in my diagram here. And t can take on any real number. Okay? Now we sometimes write this by explicitly giving the components. So if I'm talking about a general point on a line, I'm going to use xy. Okay? If I'm talking about a specific point on the line, well, we use, again, the naught notation, x naught, y naught, plus t times, and what we're going to use to represent our direction vectors, we'll call it AB. Okay? And again, t can be any real number. So what this gives us here is it gives us an alternate way. So now, a third way of defining the equation of a line in 2 dimensions. But what I'm hoping that you're going to see is that this is the method that's going to allow us to bump it up to 3D. All right? So if we take a look at this example here, if I give you a point on the line, and now instead of giving you a slope, I'm giving you a vector parallel to the line. So this is going to represent my R naught as a vector. So from 0, 0 to this point, this is going to represent my direction vector. So the equation that represents this line is just going to be R equals my vector to my known point, negative 3, 5, plus t times my direction vector, okay, where t is any real number. Okay, and if I want to calculate different points on this line, I just choose different values of t. And of course, I can bring this all together by distributing t and then adding it to the vector to the known point. All right, so again, why do we bring up yet another way of defining, we had two other nice equations for a line in 2D, because this is the one that I can now easily upgrade to 3D, all right? Because now we're going to do the same thing. We're looking for any point on this line. We're going to be given a specific point on the line, and ABC is going to represent our direction vector, which is some vector parallel to the line. So I'm going to draw essentially the same diagram as before, except in 3D. Okay. So let's say I've got some line in 3D. Okay. I'm going to start with my vector from 0, 0, 0 to some known point on the line. That's going to be my R naught. Okay, I'm going to use any vector parallel to the line. That's my direction vector. I'm going to add some scalar multiple of my direction vector, and that's going to produce some other general point on the line. Okay, and we see that, this represents any point on the line. Okay, so again, it's a sum of vectors. This vector R naught plus this vector Tm produces some general vector to a point on the line. And by changing the value of t, including negative numbers, I can define any point on this line. Okay, so we've got M, which we're going to represent by ABC, is our direction vector. And what's special about it is it's parallel to the line. Okay, then we've got our scalar multiples, okay, that we're multiplying to the direction vector. They can take on any real values. Okay, then you need your vector to a specific point on the line. So this is we'll say known, we'll say it's a vector to a known point, because again, these are all vectors. So this is a vector to a known point on the line. Okay, and then we've got the vector r, which represents any point. Okay, it's like our variable yx. Okay, this will represent by x, y, z is the vector to any point on the line. Okay, so here, if we write this out, this is what we call the vector equation of the line. And not surprisingly, we have r is equal to r naught plus t times m, our direction vector. And of course, t can be any real number. Sometimes it's written out with these components explicitly given. So x, y, z, which is a vector to any point on the line, is x naught, y naught, z naught, plus t times our direction vector, a, b, c. So these are what we call the vector equation of the line. And sometimes we write it out with each individual component given as its own equation. Okay, so here, if I'm looking for the x component of a point on the line, well, what's that given by? It's just given by x naught plus t times a. So essentially, it's just using my characteristics of vectors of scalar multiplication and then vector addition, and that's just the x component. And then the y component is given as y naught plus tb, and then our z component is z naught plus tc. And this is what we call the parametric. Parametric equation of the line. Okay, and we call t the parameter. This is the thing that's changing. As I change t, I get new points on this line. Okay, so again, sometimes it's good to reconsider an old problem so that you can more easily generalize it to 3D. All right, and we'll end off by looking at this example here. It says find two vector equations to represent the line passing through A and B, these points A and B, and then rewrite one of them in parametric and, oh, I should have taken this off, so we're not going to do symmetric form. Okay, there's a third form. You're welcome to look at it in the textbook, but we're going to stick to vector and parametric. Okay, so the first thing I need is I need a vector that's parallel to the line. But if A and B are on this line, well, it makes sense that the vector joining them is going to be parallel to the line. Of course, the vector BA would also be parallel to the line. But when you think about it, any scalar multiple of AB or BA would also be parallel to the line. So this is where you start to see that there's lots of different equations you could write for a line in 3D, depending on what you choose as your direction vector and depending on what you choose as your known point. Okay, but in the end, they all represent the same line. Okay, so let's start by finding our one direction vector. So let's say we take the vector AB. So what do we have? Remember, second minus first, so -1 minus 2 is -3. And here -5 plus 3, because minus -3 is going to be -2. And then 0 minus 6 is -6. So there's one direction vector. I could have done BA, which would have given me 3, 2, 6. Okay, I could take double this, 6, 4, 12, and so on and so forth. Okay, and of course I can use either A or B as my starting point. So if I want to write a bunch of equations, I'll actually write 3 of them. So one of them could be R as a vector equation is equal to, let me start with that as the given point. So vector to that point, 2, -3, 6, plus T times, let me use 3, 2, 6. Okay, this would also work. 2, -3, 6, plus T times 6, 4, 12. That would be perfectly good too. Okay, or I could start with the other point, -1, -5, 0, plus T times, well, let me go back to 3, 2, 6. And of course, in all of these, T can be any real number. So any of these are reasonable equations for the line. Okay, so if your answer doesn't look exactly like the one in the textbook or what a friend of yours gets, check to see that your direction vector is parallel to what they have, and check that that point might also be on the line. And if I pick the first one to write it in parametric form, well, the x component of a point on the line, in this case here, would be given by 2 plus 3t. Okay, the y component would be given by -3 plus 2t. And the z component would be given by 6 plus 6t. Okay, so now what we have is we have a way of representing a line in 3D. Okay, and as you would have done back in grade 9, the next step might be, okay, I'm not going to get there right away, but eventually you're going to start to see what happens when you intersect two lines. how do you determine that intersection? Clearly, it's going to have to be a slightly different procedure as what we had in the past because the format that we're using is a little different. Okay, and that's it for this week.